Good afternoon, folks, and welcome to another installment of the TU McDougall School of Petroleum Engineering Graduate Seminar Series for the Spring 2022 semester. It's a pleasure to introduce to you today our speaker, Dr. Quanlin Zhou. Dr. Zhou is a staff scientist with the Lawrence Berkeley National Lab. And he's graciously accepted our invitation to present some of his work in the area, pertaining to geologic sequestration of carbon dioxide, a timely and important topic. And I know I, for one, am really eager to learn more from Dr. Zhou about this subject. Dr. Zhou received his doctoral degree from Technion in Israel and has spent much time working in both theoretical methods, both analytical and numerical, on multi-phase fluid flows, fractured media, and of course, over the last 15 years on carbon sequestration. So once again, I'd just like to remind attendees really quickly, please mute your microphones during the presentation. At the end of the presentation, we'll have a Q&A session, and I invite you to use the raise my hand facility that's done by clicking the icon in the middle bottom of your screen. And I'll call upon you by name in order for you to unmute yourself to ask your question. And please remember to remute after you're done speaking. Without further delay, Dr. Zhou.
Okay, thank you. Just let me get shared. You can see my screen, yeah?
Yes.
Okay. Thank you, Dr. Remy Yunis, for this great opportunity. I'm honored to talk to you, the graduate students and the faculty members at the University of Tulsa. So today I will share with you my 15-year research in geological carbon storage, GCS, with 3 challenges in partial propagation, CO2 channeling, and thermal fracturing. I will also give you broad background on the 3 dynamic processes at different scales. So it has been 30 years of GCS research, demonstration, and development since the first international conference in 1992. Significant advances have been made in laboratory experiments, analytical and numerical modeling, and field demonstration and monitoring. So for me, I'm very fortunate to work with 3 students on experiments, 4 or 5 postdocs on modeling, and global colleagues on field projects in the red pink stars. So domestic and international. So even though the pore space, you see the pore space in sedimentary basins is huge, but some projects didn't meet their experiments because of injectivity and leakage issues. For example, for the Big Sky project at Cape Doe, so no CO2 injection was done because of the low injectivity and productivity for CO2. For the Insana project, the industry scale CO2 injection had to stop after 7 years because of the fracturing and also fault opening in the car park. But there are a lot of projects with a lot of monitoring data, which I get benefit from that. So I will show you some slides of such data at like a cornfield in Mississippi and the Carter in Illinois Basin, and also the Erdos in China, that project. So from this field project, I found some like knowledge gaps for my own research. So for a typical storage complex, there are like a sandstone car park, sandstone car park, and also basement rock and USDW to be protected. So we also have injection weir and liquid weirs, and sometimes we have faults for the car park and above, like sails above. So when CO2 is injected into the underground, so we know the pressure propagation in the storage formation and also into other formations, so the diffuse leakage, so the car park, and also sails, and also Fox leakage, so webbles into other formations. So that means like a pressure plume is very significant in the lateral and in the vertical directions. For the CO2 plume, so which is much smaller in this red, like in yellow side color, but sometimes may be much bigger than what we predicted by numeric modeling because of the channeling, spreading, invasion, and the breakthrough. We call the CSIB process because of the heterogeneity. And the last one is for the near wearable phenomena. Sometimes the cold CO2 is injected, and then we have like a heat conduction and convection near the wearable in the storage formation, and also the heat conduction in the car park. So that means we may have cooling, and sometimes with strong like thermal stress, and possible we have like thermal fracturing. So all these three different processes or phenomena, they are at very different scales. So for pressure, very large scale, and for CO2 plume is the intermediate scale, and for thermal fracturing, that is near wearable. So now for the three challenges, I will first talk about the pressure propagation with the analytical modeling. So in the multi-layer basin, and with some observations from the Illinois basin from the field project, that gave us some ideas on how they exactly not only modeling but also the monitoring data show us how pressure propagation in the storage complex. And then finally, I will show you like a numeric modeling of basin scale deployment of CO2 storage in the Illinois basin. That's back more than a decade ago. We did that modeling. And then for this CO2 channeling in heterogeneous formations, I will show you like two examples. One is a laboratory experiment in like a meter scale sandbox, and the other one is a field testing at the cornfield, Mississippi. So finally, I will talk about the CO2, the thermal fracturing at a CO2 storage site. That is, so this phenomenon has been overlooked by the entire community for decades. So we are very fortunate to get a chance to do some modeling work with some field evidence from the field, and I will show some significant, especially for US, because of the high temperature at depth. So finally, I will show some theoretical modeling of thermal fracturings in 3 cases. And for the first topic, for partial propagation, so here again, this is a multi-layer system. So we have a sandstone or aquifer and a shear or sealing unit and the aquitard. So in most of sedimentary basin, we have many formations. We also have many injection wells and liquid wells. So that means we need to do the modeling for this type of storage complex for that. So the existing solutions, they either focus on this aqueduct diffusion, like diffuse leakage, like this, without leakage wearable considered, and also wearable leakage by some studies without consider the diffuse leakage. For us, we combine these two together to develop analytic solutions. But so the fundamental solutions in the Laplace domain is very clear. This is the zero order modified Bessel function of the second kind. So the format is similar. This is for the one like a sandstone formation or one aquifer. So for diffuse leakage in multi-layer systems, we have like a governing equations. This is 1D radial flow for aquifers, and then 1D vertical flow for the aquitard. So they coupled by the leakage rate at the interface. So when we put all together for all this aquifer aquitard, we have this system. That's in the Laplace domain again. So that is the ODE. And then we have this eigenvalue and eigenvectors. We can calculate that. And then for the solution part, you can see that again, this is a Bessel function, modified Bessel function, the same. And then we have this eigenvalue and eigen vectors in this solution so that's n is the number of aquifers. So the aquitard solution is like this, just depends on the overlying and the underlying aquifers. And so this is without the focus leakage. But for the focus leakage, so we need to consider the wearable continuity equations. So this means how much is in is how much is out. Like so, the wearable upward and downward flow, and this is the continuity equations. And so also we have a boundary condition here into around the wearable. So the liquid wearables. So the T is the total drawdown or the partial buildup, and then L is the leakage. So that means for this system, we have these algebraic equations. So we can solve all this for unknowns. It's this one for the liquid wearables. So when we put everything together for the focus leakage and the diffuse leakage, we have these solutions for the aquifer. So that is the partial change in the aquifers. This first term is for injection-induced partial so this N again is the number of aquifers. This Ni is the injection well, number of injection well, and the Na is the number of liquid wells. So this term is is where leakage induced pressure change. So you can see again, this is the fundamental solution. The basic function is the same. And so we can also calculate the diffuse leakage. So the interface between aquifers and aquitard, again, we have two terms. So the first term and this leakage induced term. So, and then we can also calculate total flux leakage rate. So the many leakage wells in the at the interface or into a aquifers. So here are two examples. So the first examples we have like 8 aquifers, 7 aquitard, 1 injection well, and 1 leakage well. So that is the system. And so the red profile is the pressure change without leakage well bore. So with like a diffuse leakage only, without flux leakage. And then for other 3, we have like a different leakage well permeability. So that this one, the permeability is the highest one, and this one is the lowest one for these 3 cases. We can see that we can calculate this. The profiles are located at the like 10 meters from the leakage well and like 1990 meters from the injection well. So that is a diffuse leakage for the different at the top of different aquifers, and also flux leakage at the top of different aquifers. We can calculate it very easily for that. So on the right side is another example. So that means in this example we have 5 injection wells and a cluster of leakage wells in this field. So this is pressure change control is in the storage reservoir. That means injection reservoir. And then this is in aquifer 5 above the injection reservoir. So that I believe this is at the 30 years of CO2 injection. In this case, we only simulated the single phase flow. We didn't do the 2-phase flow modeling because our focus is on the large scale pressure propagation, because the pressure plume is significantly larger than CO2 plume. So here is one example, because I like the data a lot from the field. So this is the multi-well, multi-level pressure and temperature monitoring at Decatur by 2 projects. So here you see that's CCS1, CCS2. They inject 1 million ton CO2 in 3 years. And then they did another, like from 2017, they have a CCS2, VW2. So that like an injection well and monitoring well. So for industry scale CO2 injection at this site. So you can see at each well, like VW2, we have 5 gauges for pressure and temperature. And then on the right side, that is like several years monitoring of the pressure data at different gauges. You can see that. So this gave us a very unique data set to understand like a pressure propagation in multi-layer systems. You see, we can have many like a unit, hydrological units in the Mount Simon sandstone. That is the storage formation and the car park here. So for us, this is ongoing research. We want to combine the analytical solution with the multi-rate memory function we developed for heat transfer to consider the effect of heterogeneity and sand channels in the multi-layered Mount Simon sandstones. So modeling and the data give you some sense of how propagation CO pressure, how far and how how big, so the pressure propagation. So for the numeric modeling, we did in 2009 and 8. So that is the Illinois Basin, and then that is the core injection area suitable for CO2 injection, and then that we have 20 injection wells with a spacing about 27 kilometers and 30 kilometers in the north. So that is the district. We worked with the Illinois Geological Survey, and the contour is for the, I believe, is the top of Mount Simon, and that you can see the Mount Simon is up deep to the north, and this area is in Chicago area, so with a lot of groundwater pumping. For us, our focus was to understand the pressure propagation in a full-scale deployment of CO2 storage. So that means we inject CO2 a lot, so 5 million tons per year per site for over 50 years. So that is about 1/3 of large stationary CO2 emission from the area. So we know Mount Simon is perfect for CO2 injection. So you can see the thickness is very thick. It's up to 700 meters, and then they up to the north. And at that time, we only have one well with the data. So we use that with the support from ISGS Geological Survey. We get the sublayers in the Mount Simon sandstone, and then this is the injection zone with high permeability, high porosity. And so for here, we have this kind of permeability and permeability in the basin based on the data from many natural gas storage sites, because they have the permeability and porosity. We use that to map the spatial distribution. And then this is just a numerical grid for 2D, and we use 1.2 million grid block to do the modeling with TAF2MP, the parent version of TAF. And so there, here are some kind of results. On the left side is pressure buildup in bar. So we can see here this high pressure increase in this region. So the maximum is about 35 bars. And here in the Chicago area, we don't have much pressure buildup. So on the other side, for the analog, we have this pumping induced drawdown in the Chicago area. So you see that's the pumping rate over more than 1 century. So you can compare with these two. So again, because this one may be more closed system in the, and then this one maybe there's some opening for the Mount Simon sandstone. So kind of the magnitude is kind of on the similar 30, 35 or 20 bars here. And here are the evolution of 3D CO2 plume. So here is 50 years and 20 years, 200 years. You can see the spacing is about 30 and 25. So that you can see maybe several kilometers, in the plan view. And then that is 200 years. You see that's much larger, the CO2 plume. And on the left side is the cross section. I think it is number 10 in the north-south directions. We can see CO2 CO2 was injected in this zone, and then we can see CO2 plume spreading, and we also can see CO2 invasion and breakthrough to different units, all the way to the top of Mount Simon. Here is the top of Mount Simon. We also can see the channelized flow in the high permeability layers inside the Mount Simon. So here, so for the second topic about the CO2 flow channeling, so so that is like a laboratory experiment. We can see this is the car park, and then this is the sand unit, and we also have like a regional flow. That is the this is the injection well, and this is the homogeneous case. And so for heterogeneous case, we have this one, and you can see here is high permeability zones here, and the yellow is low permeability zones. So you can see that is separate all that, but for the experiment, you can see this is spreading or channeling in these high permeability zones, but then that is the second body of CO2 plume. So it seems you don't have CO2, but that is connected because the CO2 is only way to the north, to the up in this direction. And so again, that is kind of I call the pocket trapping. So that is the CO2 plume in the high permeability zones from here. And then finally, everywhere you have CO2. So it seems you can, there's a discontinuity, but the CO2, we have the CO2 invasion and breakthrough into the yellow color, that is the relatively low permeability phases. So that is kind of give you the idea of the channeling, spreading, invasion, and the breakthrough. I call the CSIB process. Now, if we move to the field, so that is in quant field. So 3D seismic give us ideas on the like a sand channel and the pond water system. That is the testing site, the DAS site. So at this site, we have a F1 injection well and F2, F3 are two monitoring wells, like spacing about 70 meters, 34 meters. So from the well logs, we can see the sand D and the sand E separated by buffer, all between the three wellbores. But the key is the continuity of the buffer. Now for the test, we have a 3-step CO2 injection rate, like this, and this, and here. You can see 3 steps. But we also have a CO2 like a tracer release at a different time, so like at a different rate. You can see here early time, and it's the second step and the third step. So the bottom figure shows us how we get monitoring data, like a tracer test sampling. It is for the 3 tests, and the flow meter. So that means we in the vertical direction we can see how injected CO2 distributed along the wellbore, and the DTS distributed temperature sensor monitoring, and the RST, that's a reservoir saturation tools, like a snapshot, and it's 3D seismic, cross well seismic, and the continuous ERT data. Like every day we have data for that. So that is all the data. And for me, I get data from like different groups, and then put it together. Because when they do this, their research, they just focus on like 3D seismic data, or cross well seismic data, or RST data, wellbore monitoring. But so for me, I came up with like a high level picture of multi-scale CO2 flow channels. So here you see that is a flowway channel, and then there's a pond bar, and we have a hydronic barrier. So that is from 4D seismic survey. So like F1, F2, F3 are located in the pond bar, but F3 is next to the hydronic barrier. So at any time, injected CO2 through this one channel to 3 channels in F2 to 4 channels to F3. So we can see from the tracer test data and the ERT image, but at night time, the injected CO2 also flows to this way, to the large scale channels L1 and along the flowway channel and back to M1, the intermediate scale channels, back to the cross section. So again, this is supported by the tracer test data. So when people saw the tracer test data, they saw, oh, there must be some multiple flow paths, but they don't know where the flow paths are. So for us, we put all the together in this space, the channels. For example, for this is the tracer test data. Like the F2 arrival time, like a brick circle with the F2 and the F3. And you can see you have two channels. And here you have 4 channels. That is early time. And then late time, the arrival time is equal. You see, that is for the 2 variables, they are equal. And then at late time, so the like F2, even the arrival time is later than F3. So that means from this, you can see must be multiple flow paths, but they didn't know where. So so for the small scale channels, we can see this is F1 because the like a flow meter log, and this temperature log, and the CO2 plume. This is spread, but this is more sharp, very narrow channels. This F2, like 3 channels at a different time. That is RST logs, and the F3 we have 4 channels at the early and the late time. So this just give you one point in the space, but how you link this all together, yeah. So this is ERT data. So you can see that is across the buffer. So that means the buffer is discontinuous. So you can see here the arrival time, and then here is like a hydronic barrier. That is accumulation and spreading at that. So that means the CO2 cannot go beyond the F2, F3, that hydronic barrier. And then from here, so this just gives us a cross section. And so here we can see, because there's a hydronic barrier, that the top and the bottom is no flow for CO2. So that means the CO2 must be go to the second direction, so perpendicular to the cross section. So we lost CO2 in this with time, and then we gain CO2 also with time. You see, so that means they change the flow direction in the third direction, perpendicular to the cross section. Now, so that is the cross section seismic data. That is the velocity change. You can see the flow channels between the F2 and the F3 very clearly. But we don't have that data. We only have a baseline data between F1 and F2. But for the 3D, so that is for the cross section. But for the 3D seismic, you can see channel now. You can see that is the image. And so that is there are 3 variables, and there's a hydronic barrier. So that means when we put everything together, we can see the channelized CO2 flow, sand channels, like all this data set support this high level picture of that. So let's see. Okay. The last topic is about thermal factory. Again, this phenomenon has been overlooked by the CCS community for decades, even though we know in petroleum engineering back into 1980s. So thermal factoring was first proposed to understand the injectivity, enhance the injectivity in water flooding and in like Alaska fields. So, but for geothermal, we use this thermal stimulation to enhance the productivity and the injectivity. But as for CO2 storage, so nobody paid attention on thermal factoring. So for me, is my first hand like data of my understanding is from field, and then especially for this outdoors side. For example, for that is liquid CO2 injection. Here is close to like 0 degrees C. Even here is minus 13 degrees C injected CO2. And then that is cooling. You see, this is the background temperature, and this is cooling. You can see here cooling, and then there's enhanced injectivity here. So very interesting. They did this like a production logging every year. They did that to understand how the different layers they flow through different layers. They found this kind of finally they just along the top layer inject like 90% injected CO2 through this. And again, this is cornfield data. So you see that is the injection rate, but this is temperature. You see, the cooling is about like 60 degrees C, but this is pressure change increase. So no modeling could match this pressure. So at that time, like UT Austin, there's like a Said, they mentioned maybe there's thermal effect or the thermal mechanical effect. So my understanding is there must be some kind of thermal factoring at this site. So that means your injectivity is higher. And then this is the Aquifers. That is independent from the, when I saw that, oh, they found the same similar. So you can see that is the pressure temperature. I believe that is, let's see, I don't think that is cooling, but that is, I believe that's injected CO2 temperature. If it's very cold, so you have this higher injectivity index, and then here it's normal. So that means without much thermal effect or thermal factoring effect. So we from here we now for CCS we do have this field evidence from the field to show the thermal factoring and their effect on the injectivity and also flow channel at different depths. So that is from the field. Now, when I put all this together with like temperature at depth, so they did that. A lot of geothermal variables, like petroleum variables, they put all the data together. So you can see this is the high temperatures, and then even though here that is the EGS site, here some like that's you at Utah, they got a forge site here, and so here the red star, like the black stars are carbon safe projects, the locations, and then this we know here is the Aquifers, and here is the cornfield. We know that we have some fracturing issue, so you can see except this one, we all located at the high temperature at depths site. So that means maybe the CO2 storage, for CO2 storage, the thermal fracturing is significant for this. And so for us, for me, always I want to do the fundamental study to get this better understanding, and then we finally get identify this like a half plane thermal fractures from hydronic fracture of 4, and radial thermal fracture around a horizontal weir, and longitudinal thermal fracture along the vertical weir bolts. So we did this, and Bin Chen was a postdoc with me. So we get like my concept with his modeling scales. I'm not geomechanic guy, and he is like a fracturing guy. So we work together to get, and so that is examples, the conceptual. And today I don't have much time to talk about all these things, but I show you the concept. You see, for the thermal fracturing, they are very different. This is hydronic fracture, and this is thermal fracture, like a half plane thermal fracture. Some fracture are arrested because of the interaction between different fractures, stress interaction. And then this is the propagation fractures, and this is arrest fractures. So that means we have a dynamic spacing, we have a dynamic length, and we have dynamic apertures. We need to do the modeling. So of course, because this is analytical solutions, we need some assumptions. And so all that, I think I don't have much time for that. I just show you for single fractures, you can see, because we only have one parameters. Okay, this T. That is when we do this dimensionless solution, we only have one parameters. That's T. You see, that's a solution chain with a function of T, and then we have a scaling law. So that means at the night time, that's all straight line, square root of T. That is solutions. And this part we can calculate analytically for this. And then for constant spacing, that means we force this spacing no change, and then we do the modeling, because this is one step we need for dynamic spacing solutions. You can see that it's a single, like a single fracture solution, and so you can see the stress interaction slow down fracture propagation. And so that is a dynamic solutions. We can see again this single fracture solution, that is a constant spacing, and then pink are dynamic solutions. So that is the solution we are interested in. And then if you say, okay, you are interested in a fracture pattern, so that means when you get that is a arrest line. So that means some part of half of the fractures are arrested and half and propagate. Finally, maybe just the 4 fractures at this time. And so that you can see the fracture patterns for that. So that is the solution, dimensionless solutions for the fracture spacing, fracture length, and the fracture aperture at the surface, cooling surface. So again, for the length, we have this scaling laws. And so that is the fracture patterns. Well, we do for the mod, but this is the mode 1 fracture pattern, and then based on this forge side. So here T equals 0.11. That means it is a in situ pressure. So that means at this site, the thermal fracture fracturing is easier for that. That is in the dimensional space, we have fracture spacing length and also aperture. You see, they compare with our solution, and the dots are numeric solutions. You can see arrested and change and arrest, and then this is like propagating fractures. And then when we enhance and weight the injection pressure, you can have this. But in this case, again, the driving force is thermal stress, not fracture, not like fluid pressure. And for the radial, like a horizontal wable, we have a cased wable, we have like an open wable. We can also do the simulations for this, and then this is the fracture pattern. So I think that is the let's see, this is the spacing length and the aperture for the dimensional solution, and then this is the pattern. But the fracture length is shorter than the half plane solutions, and then this is again this spacing and the numerical and the analytical solution, they compare with each other. And then finally, this is the longitudinal fractures. In this case, we have two cases. One is two-wing fractures. So that means for highly anisotropy stress, we have this pattern. And for constant like isotropic stress, we have this kind of pattern. So for any solutions, that is between these two solutions. This is the numeric solutions, and then this is the analytical solutions. You can see finally they follow this like two-wing solutions. At the early time, that is they have more like multiple fractures. So you can see the transition to this, and then this is the apertures. So and finally, that is a comparison between these three different cases. We can see the half plane is longer. You see that's the fracture length, and the radial is in between, and then two-wing is shortest for this fracture length, and also this aperture. We have the skeleton for this. So this Q is different. You see that is the square root tau, but the tau is dimensional time, and then we have this and here. So that depends on the dimensional stress. That's a T, and then we have this coefficient, scaling coefficient. That is scaling. I think the exponent that. And here is I believe so is 50 minutes. Here are the summary of the three different challenge, also different areas of research. I just leave here. I stop here for questions. Thank you.
Thank you, Dr. Zhou, for an excellent presentation. We have time for questions. So once again, if members of the audience have a question, please raise your hand. I'll call on you. And maybe while people think of questions, I have one. In your thermal fracturing analysis, it seems like the stress communication, if you will, between fractures is what's causing the localization instability. You know, some fractures shorter than others, they arrest. Did you take into account the energy balance or leak off into the rock in between fractures?
Yeah, so in this case, we didn't consider leak off. We only consider the like heat conduction here. So for like a convective and conductive heat transfer, we may not have that solution in the so because this is more complicated. You see, we also get like a review comments. Okay, that change everything. You see, if you have flow good leak off, so that means the thermal transfer is also changed, and so that is maybe the only numeric solution can do this kind of modeling, and not the theoretical studies. So for us, we neglected thermal convection, and then we only focus on the. So here, I think here we neglected thermal convection. So in this case, I know for geothermal it works because it's a granite, and so that means we may have a very small convections in granite. So this concept, I think, was first proposed to enhance heat transfer area in EGS, enhanced geothermal system, back in 1970s. And so like Patrick, from UT Austin, they had some idea for like an unconventional share. They proposed a similar like so concept for their study. Yeah.
Great. So yeah, so probably it wouldn't affect the conclusions with respect to this localization instability, but then the scaling laws that you develop are essentially conservative estimates. One might expect. Is that correct?
Yes. Yes. Okay. Remy, on the other side, I did like a heat transfer modeling in fractured reservoir. So even though if that is the fractures, infinite fractures, when you have like a thermal perturbation into here, so you have convection and also conduction in that you leak off. So this part, like penetration depth, may not be that big. So because of the significant area for the heat transfer between the fracture and the matrix. So for the modeling, yes, especially for fractures, so the depth for thermal perturbation is not that big, but it's bigger than what the conduction gave us. So in between, yeah.
Yeah, so I'm thinking, you know, for a practical application, actually the scaling laws you develop are good. You know, in engineering, we usually put safety factors, you know, and we want to over-engineer. So actually using those scaling laws, you know, to avoid fracturing further out, you know, those would be conservative estimates that one can use as a safety factor for a CO2 application as well.
Yes, I agree. So that's our future step. We want to, especially I try to get some funding for this. Like I did contact with like DOE managers, with the EGS and also CO2 storage. Try to get some funding and hire a new postdoc to work on numeric modeling to understand all these different the effect of different assumptions. That's one, and the other one is we do have like monitoring data from different sites. If we can like enhance our understanding of thermal fracturing, that will be great. Yeah.
Great, thank you. All right, questions from the audience, especially graduate students. Don't be shy. So maybe
yeah.
Go
ahead.
Hi, Dr. Zhou. Thanks for your quite interesting presentation. It's my first time to know the thermal fracturing, so I want to know what's the mechanism of the thermal fracturing. Is it because of the rock will be colored and the rock will be easily broken, or the carbon dioxide will be heated and the pressure of carbon dioxide will increase.
Okay, so for example, for we say okay for the corn field, because we have data. So the injected CO2 is on the surface, yeah, it's a normal temperature, and but the reservoir is very hot, 128 degrees C. Even though we have some heat loss around the wellbore when you inject from the surface to the reservoir, still you can see the temperature, you see, from 128 degrees C or 132 degrees C to like 73 degrees C, you can see at the reservoir. Okay, so that is cooling. So the cooling will induce significant thermal stress around the wellbore, and then they may induce fracturing for that.
Because you inject the liquid carbon dioxide, will it be heated and become to the gas and increase the pressure?
So here is these two sites. The CO2 injected is normal temperature on the surface. Okay, maybe 30 degrees C or 40 degrees C. But here in China, the Erdos site, that is liquid. So, but you know that you have a pressure and a temperature, yeah. So the two effect. When in the wellbore, you got to do this. If you want to do modeling, you got to simulate this heat exchange with the wellbore surrounding rock and also inside the wellbore. And then, but this is the data from the bottom hole. You get the temperature. So that is give you the exactly cooling, the degree of cooling at the depth of reservoir, storage reservoir.
Thank you, Dr. Zhou.
Yes, they are coupled. So always they are coupled. So
yeah, thank you. I got it.
yeah.
More questions for Dr. Zhou. So I've got sort of a maybe more of a big picture question. You know, we see a lot of interest, of course, given the importance of this subject, a lot of interest from the DOE and other agencies to go ahead and perform, you know, site selection, site characterization, to go out and to try to demonstrate at the field scale injection sites domestically. Do you think, you know, and on this slide you have lessons learned, project failures, and knowledge gaps. Do you think today, at this point, there are still some important knowledge gaps that can be worth studying? Maybe, you know, short term, over 30 years versus long term, and so on, sort of as motivation for our current generation of students who may pursue research pertaining to GCS.
Yes, I believe there's some gaps. Yeah. So even though my understanding is that we have the most people, they don't pay much attention on what we can learn from field. So because when you collect the data, that is time consuming, and sometimes you don't, some sites you don't have new insights, but some sites you may have that's some good insights. Yeah. So that's the biggest gap. Modeling, they just do modeling, and then the field guys, so they don't. Sometimes they don't work together, and sometimes especially challenge when we do the modeling for the field projects. So that's I always like, for example, for corn field, I don't do the modeling. My first step is to understand the data, what we can get from the data. So that is the many modelers, they don't want to spend their time in that. So of course, I tell you, the DOE has supported many projects for drilling, but not many injection wells were used for CO2 injection because of the complexity in the subsurface. We don't know much, especially sometimes the injectivity is too low, and we cannot inject any CO2. That happened. Not in real time, real cases, but many, it's kind of often we have that problems for that. My understanding is maybe at the beginning we estimate the capacity for storage is too high. That is my understanding. But for a knowledge gap, we do the best is to work with the field guy to get the better understanding. Okay, for example, for this one, in Sana, yeah, I have not touched that because this is horizontal web. They have 3 horizontal web. You see here, and then they have factoring and they call it fault opening. But I tell you what the modeling they did. They did the modeling. They assume the existing fault, but they don't read the drilling report. So the drilling report didn't show any fault at that location. So there are many things like that. The modeling is just modeling. Sometimes I don't appreciate their modeling. So they just assume we have data. My job is to match the data, and then they don't read the drilling report. That's anyway. So for me, it's kind of I learned from the field, and I came up some concept for knowledge gaps, and so we do there's some kind of fundamental modeling. That is what I'm interested in. Yeah.
Yes, thank you. Okay, so any more questions from the audience? Dr. Liu.
Hi, Dr. Zhou, thanks for your presentation. Very interesting and very informative. I do have a question about the thermal fracturing.
Yeah.
Does this thermal fracturing only happen in the near wellbore region or further deep into the formation?
So if for injection, that is near the wellbore, because we now let's say so this is near the wellbore, yeah. So for this one is about 30 years. That is about 80 meters. That's now. But this one, we have that that is near wellbore for the for the injection, vertical wellbore or horizontal wellbore. That's But the reason is that let's say if we go back to this diagram, if we have some fractures in the cap arc, you will have leakage here. So like injected CO2 leakage, so that into the So that is all the near wellbore effect for this. But maybe in the reservoir, away from that, because of convection, and maybe your fracture is longer than what we predicted. So, but still not very far. We did the modeling for thermal transfer. So thermal perturbation is not further away, but from the geothermal field, sometimes we observe, like the community observe, like a early breakthrough curve. So that means your production, the temperature of your produced water decrease with time. So that means you have a breakthrough for thermal. So that is far away. But for thermal fractures, that domain should be smaller than the thermal perturbation.
I see. Thanks. Another question is what is the temperature range for the majority of the CO2 storage sites?
Oh, so I think
for the most of the sites. Yeah, I mean there's always exception like a very high temperature, but what are the temperature range for the majority of the?
So okay, for example, I just show some example, yeah, and so here this temperature is small, even though they didn't inject any CO2 over there. We know the temperature, but so this temperature is it's about 50 degrees C in the reservoir, and this is high, that is about 132 degrees C, and so this is just 50 something, but they injecting liquid CO2. Here is 95 degrees C in the reservoir. The cooling is about 40 degrees C, and this is Kaizen site is small. It's small. I didn't do all this. I think I should have all this data. I didn't put all these different sites with different temperature. so I think I should do that. Yeah, but this, okay, this is surprising me. When I got this map, that is at depth of 3.5 kilometers. You can see Eagle Fault is here. Yeah, Eagle Fault. And Hennesville, yeah, Hennesville is here. That's all in high temperature zone. So Eagle Fault they should have some problems for thermal fracturing. And for this horizontal webers, I learned from Eagle Fault the ConocoPhillips they did a pilot test in there. Their cooling is up to 120 degrees C. That's very significant in Eagle Fault. Yeah.
I see. Thank you very much.
You're welcome.
I've got a question from Lucas Hornbrook.
Yeah.
Hi, Dr. Zhou. Really liked the presentation. I might have missed this, but is there major performance differences between the injection of CO2 gas and CO2 liquid, or are all these cases the injection of CO2 in liquid form?
Not urine is a supercritical form. Let me go back to this. Okay. Here, so this side is liquid CO2. That's those in China. That's the only side with that. And I know this slipper in the top of the Weber. That is a two-phase flow regime. Because the temperature is very low. Yeah, that is in the North Sea. And the urine is supercritical CO2 because high injection pressure at the wellhead. So there's no much change in phase in the well for injection well. So, but sometimes we do for Kelvin dome because they try to produce CO2 from the dome and then produce the CO2 in the brine flake. So when they produce the CO2, they have like a phase change from liquid CO2 to supercritical CO2. And then they induce a lot of cooling here when they produce the CO2 here because of phase change. And so because they want to get a very deep because of the efficiency of storage, they don't use the gas CO2.
Are there major performance differences in the thermal fracturing between the injection of gas versus the supercritical fluid or the liquid flow?
Oh, that part? Let me see. So there's some change in like fluid properties, supercritical CO2, or liquid CO2, and gas CO2. That's one aspect we should consider if we wanted to see the difference in performance. That's one, and that because maybe you inject the same amount of CO2 with a different density or different phases, the cooling at the depths will be different. That's one aspect. So I didn't do the modeling for that part, but they should have some difference in cooling. So yeah.
Thank you.
You're welcome.
Right. We've got time for maybe one or two more questions. Dr. Liu?
Yeah, one more question, Dr. Zhou, for you.
Yeah.
All right. So this talk is mainly about the projects of CO2 storage in the seeding water, seeding formation, right?
Yeah,
Are there many cases that where they store store the CO2 in the depleted reservoirs or abandoned reservoir, gas oil reservoirs, I mean.
So yeah, the non-history for EOR, yeah.
I mean, the depleted hydrocarbon reservoir, are they also a good candidates or major project sites for CO2 storage?
Yes. So because I didn't show here, there's some maps in the atlas show this kind of like a depleted like a gas reservoir, depleted the oil reservoir. There's some projects they do have in the industry. They have that practice for EOR, enhanced oil recovery, for many years. Many years. So so that is sometimes even during the Trump administration, they kind of push in that direction because the DOE try to encourage the industry to do more EOR for carbon storage. So that's kind of. I'm not expert on that topic. I never touched that part for my research. Yeah.
Okay. What are the other good candidates for CO2 storage?
Oh, okay.
Besides the saline aquifer and hydrocarbon reservoir, what are the other?
So before, I think they considered like coal seam bad, yeah. So but the injectivity is very small for that type of formation, yeah. And they have like a basal formation, like in Washington State, and also in Norway or yeah, they did some experiment on that type of like a more reactive formation, and they can get a precipitation. But now is everything is changed. Before we know that in the ocean, yeah, they can the ocean CO2 storage, yeah. But now DOE try to support the like a direct remove of carbon from air. So I don't know. That's out of my expertise. So I don't know how but they do have some FOA for some ideas. Yeah.
Thanks.
You're welcome.
Great. So that's a wrap as far as the time we've allocated. We'd like to respect Dr. Zhou's time. So thank you, Dr. Zhou, for an excellent seminar. We have some faculty present. Dr. Zhou agreed, graciously offered to stick around after other guests sign off to have a brief discussion. So faculty, TU MSPE faculty, if you'd like to visit for a few minutes with Dr. Zhou, please hang on to the call. Otherwise, to the rest of us, have a great weekend.
Thank you, Remy.